Alright, I have Kill the Bit game going on this. This is the program running up here, but these 8 bits are the bits that we're supposed to kill. And the objective is to toggle one of these up just as the LED's over it to try to... If you get it wrong, then it makes a much more complicated pattern. Oh, there, I made it worse. Okay, stop, reset, run. Ah, got it. Killed the bit. Let's try that again. Stop, reset, run. Oh, no, I made it worse. Killed it. Stop, reset, run. That made it worse. Killed it. Well, at least the Kill the Bit program is working in the raw IMSAI programming environment. Toggle switches only. Alright, I'm going to try to do something here I've been meaning to do for quite a while. When I first encountered the Kill the Bits program back in the late 70s, shortly after the Altair 8800 had come out. I didn't have an Altair, but I was reading everything about it, and I remember being impressed by the first game for it, which some could argue might be the first game for a personal computer. That's debatable, but certainly an early one. And the fact that it only used 24 bytes of memory, and therefore could be toggled in pretty easily even on a rudimentary computer. It's always had a small bit of fascination for me how cleverly it was written. But the first time I tried to dissect it, I could make no sense of it at all. And then when I finally acquired an Altair a number of years ago, I dug into it and came to an accommodation with how it worked, and then promptly forgot it. And now with the recent IMSAI 8080 clone build, which I have a video on, I came back to the Kill the Bits program again and re-studied it and wrote down a bunch of notes and actually wrote up a sort of a technical document to remind myself in the future how it works. Anyway, so I'm going to try to explain it here as best as I'm able. I'm mostly going to be reading a script that I wrote so I don't stumble around a whole lot, hopefully. And I'm going to have to use a handheld camera for this. I could not figure out how to get my tripod support set up to support the camera in a position where everything I'm looking at would be legible and still allow me to see it at the same time. So let's get into it here. So here's what is often referred to as the original program listing. I'm not sure that's accurate. It's certainly been around for quite a while. This has the assembly language for the program. This is the whole program right here, with addresses and instructions and data, and then the mnemonics and some additional notations on how each of these functions work, which registers it's associated with, and so on. And then some comments over on the right, but they're very perfunctory and don't explain enough And then here is a relisting of the program in octal, which especially on the Altair makes it easier to enter because everything is set up spacing wise for octal entry. But I'm going to be doing this discussion in hexadecimal for the most part. So I've retyped the program onto this document, and I have it listed both in terms of octal address, octal opcode, and then hexadecimal address and opcode highlighted so my eyes go back to it easier than the mnemonic applicable to the 8080. I think this would also work on Z80 computers. And then an abbreviated description that's still more elaborate than the one on the page I just looked at. And then I go into a set of notes that pretty much step-by-step describe what's going on. So I've got already stuck into this video a little bit of when I was playing with the Kill the Bit program on my IMSAI right after I built it. So from that you should see how the program is supposed to work, how it looks and acts. So I'm not going to repeat that here. The program is divided into a setup section. That's about this part of it here. We're loading some stuff into a couple registers, loading more stuff, We get down to this point, and this is where the program beginning is considered to be, where it actually starts doing something at address 8 hexadecimal. And then it's pretty much a loop that repeats over and over. It just goes down, repeats, as a sort of a time delay, constantly updating the display, and then it jumps out of that and very quickly does a check of the switches to see which switches the user has operated as part of playing the game, does a quick bit of logic on it, stores the result, and then jumps right back into the loop again. So it's pretty simple what it does in theory. Now I want to go into the architecture of the 8080's registers, because that'll be necessary to understand going forward. So here's a diagram I made up of the various registers in the 8080. It has the main register set, each of which is 8 bits. There's the accumulator or A register. Then there's a register, so flags like the carry flag and some other things are in this set. There's also another 8-bit register of sorts, although I don't think Intel called it a register, but for our purposes it's a register. And that's the status register, which is output by the 8080 showing all of its most critical status bits encapsulated in an 8-bit word. Getting back to the main registers, we have 3 register pairs. There's the B and C register pair, the D and E, and the H and L. It's skipping the I and the J, but they go together. These registers can all be used independently, or they can be used in pairs. Some instructions in particular always use the H and L, and there's not much you can do about it. Most of the other ones you can be more flexible. There's also the stack pointer, which we're not going to worry about here, the program counter, which we don't have to worry about as far as this program is concerned, but just so you understand that there's these register pairs that we're treating as one 16-bit register. This is like one 16-bit, this is another 16-bit, and so on. But they are referred to by those letters. So let's go over the setup part of the program. The first thing we have to do is load a starting number into a register pair H and L, and that is used for the timing loop. It's basically a counter that the timing loop in the program is using to accumulate time. And we started out with 0, so that's why there's 2 zeros. So the first instruction is the LXI. It's a load, and it's got the information that it's going to load in the 2 bytes that follow. So these 3 bytes go together, and it's going to take that data and stick it into registers H and L. These two go into register L, these two go into register H. So we've set up H and L now. Now we have to get register D set up. In this case, we're not worried about register E. We're only really using register D. So we set it up and we move a value of 80, that's 80 hex, 80, into register D. Then we have one more thing to set up. We have to set up registers B and C. And once again, we do a load. It's the same instruction as up here. Although you may notice that this one has an opcode of 21 and this one has an opcode of 01. That's because there are different versions of the LXI instruction depending on which register pair you're writing into with the load instruction. In this case, it's 21 because we're going to H and L. In this case, it's 01 because we're going into B and C. But once again, we follow it with the 2 bytes of data, and the 8080 always orders these with the low byte first and the high byte second. Some processors do it just the other way around. So if you put these together, it ends up being address 000E hexadecimal. So now that we've got those set up, we can talk about what happens next. This 80 here is particularly useful to us at this point because the whole point of the game is to take an LED and scroll it from left to right across the display on the front of the computer, and then repeat back around and keep scrolling like a marquee. And this value in register D is the value that's going to be used for display purposes. So it's handy that it's called D. It helps remind us what it's for. If you take 80 hex and draw it out in binary, that's what you get. This is the 8 and this is the 0 in 80. So consider that you've got 8 LEDs arranged horizontally on the front of the computer. When you write this value to that, it's going to be this LED on and then 7 more LEDs that'll be off. If we had a different value in there like this, then the next LED would be on, and so forth. If multiple ones are in here, like if we change this guy to a 1, then we would display LED on, off, 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 on, off, off, off. So the next instruction we encounter is the LDAX instruction. You'll notice it's happening 4 times. So what this instruction does, and I'm going to jump to my notes here, note 4, and I wrote it out script-wise here. This is a line of code that many people will find confusing. Reading the 8080 instruction set description, this command will take the 8-bit contents of a memory address assigned per D and E. So if you treat registers D and E as a 16-bit word and then interpret that as an address and go to that address and retrieve the 8-bit data that's at that address and then write that data to the accumulator or ACC. That's what that instruction is supposed to do. Go to registers D and E, see what address is stored there, go to that address, get its contents, and stick those contents in the accumulator. However, this is just a ruse, a subterfuge. The program does not care what the data value in that memory location is, and it does not need that value to be in the accumulator. The only reason to do this operation is to get the 8080 to set its address bus to a value having the value of D in the upper 8 bits of the address. So if we go back to my little sketch here, here's the address bus. 2 bytes of 4 bits, 4 bits, 4 bits, 4 bits, right? the entire address bus, whatever it is at the moment, is copied to the 16 address LEDs on the front of the computer. So if you want to have those LEDs do something that the user can follow, you have to come up with a way to control which addresses are being accessed by the 8080. We're using this upper byte of the 16-bit word. We're using that upper byte as the display for the game. That's what the user is looking at to play the game. But it's the address bus. How does that work? Well, that's what's going on here. Even though there's nothing going on up in this part of memory, this would be higher memory up here, even though there's nothing going on there, if we keep writing to a certain address there, it'll force the address bus to be turning on certain bits there a lot. And since those bits are being used to control the LEDs, if you can get the LEDs to light up enough, then the user's persistence of vision will recognize those as visible LEDs, and the pattern will be useful to the player. So let's take that original value we had starting here. We start out the game with 80 hex, which is this pattern in binary. Again, this is a 0. That instruction that I just talked about, the LDAX instruction, that's going to registers D and E, and it's writing the value of those to the address bus so that it can go to that address and retrieve a value to stick in the accumulator. By doing so, the address bus must be having these bits set. Now, that would be controlled by D. I'm trying to get a good angle here. This part would be controlled by the value in register E. But we don't care because we're not using those to play the game. We're just worrying about this. That's why only register D in the D and E register pair is of importance to us. And that's why we only wrote that 80 hex into register D and didn't bother with register E. So by running that instruction, even though it seems to be going and getting data from memory and storing it in the accumulator, that's all just the ruse to get the address bus to this pattern and therefore turn on those LEDs on the front of the computer. But, you know, the microprocessor is fast, and it's going to do that so fast you won't even know that it's happening. The LEDs will be on for too short a period of time to see that they're on for playing the game. So that's why that instruction is done 4 times, right in a row. Bang, 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 bang. Okay? That is enough to get the LEDs to light up in that pattern enough to at least have a chance to be visible to the user. But if you just did that and then immediately moved on to the rest of the program, it would still seem to be scrolling too fast. You might be able to pick out the LED, but it'll be screaming by in its scrolling too fast to follow. You would not be able to play the game at that speed, so it's followed by a timing loop. So the first thing we do is we do this next instruction, the DAD instruction, good old dad. It takes whatever in B and C, which is, as you may recall, it's been set to 000E, so a pretty low value, and we take that value. We're not taking the contents of a memory location addressed by B and C. We're actually taking the value that's in B and C, and we're adding it arithmetically to whatever's in H and L. So a 16-bit word and a 16-bit word. Remember that we start out with H and L loaded to 0000, so nothing. So when we do this add, we've added 000E from registers B and C, and we've added it to the 0 in registers H and L, and put the result back in H and L. So now we've bumped it from 0 up to 000E. And immediately after that, oh, by the way, that's a single byte instruction, so it doesn't have any operators following it, no data. The next instruction is a jump if not carry. So we just did that little arithmetic operation, and every time you do an arithmetic operation, there's the chance that you might overflow or underflow the register. And if you do that, it's going to set a 0 bit or a carry bit, depending on which way you overflowed or underflowed. If you keep adding stuff to the register, eventually it'll get to such a high number that it will overflow. And when it does that, it will set the carry bit. And that's the only thing we're concerned about here, is have we overflowed the H and L register pair by adding to it. Well, we certainly haven't the first time we get to it, because we just added the low value of 000E to 0. So it gets to this instruction and says, well, did we set the carry bit? No, we didn't. Okay. So we do the jump command. And it takes us back to, remember the low byte is first, so 0008 is the address. And that's the point that I identified earlier as the beginning of the program, the part that runs after the setup part. So we just go back to the beginning. We immediately take the value in D and copy it back to the address bus and therefore to the LEDs 4 more times. We add the value in B and C again to H and L. Check to see if it overflowed by checking the carry bit. If it did not, jump back to 8 and do it again. So we do this little piece of the program over and over and over a whole bunch of times. And at the speed the processor runs, that's going to have the requisite amount of time that's desirable to have the scrolling happen at a rate that's manageable by the user playing the game. Eventually, however, we will max out that 16-bit register H and L, and therefore it will overflow and it will set the carry bit. And then, because we check it with this jump if not carry, we can't do the jump now because there is a carry. So now it just progresses on to the next byte of the program, the next instruction, which is an input instruction. Now here I have to talk a little bit about how the computer, either the Altair 8800 or the IMSAI 8080, they both do it the same way because one is a clone of the other. The 8080 processor, microprocessor, does not have memory mapped I/O. So unlike a lot of more modern processors which just use memory mapped I/O, a lot of the older processors had special commands and functionality for handling communications with I/O devices, input, output. And then otherwise, if you weren't doing those particular functions, then everything was assumed to be in the memory map, addressed and handled as memory, even if it isn't memory. The 8080 does it by having 256 ins and 256 outs. These are 8-bit I/O devices, and there can be quite a lot of them, as you can see, probably more than you would ever need. Because they only go up to that, which is actually in the range of 0 to 255, which in hexadecimal is 0, 0 to FF, you're essentially addressing the input devices or the output devices. So what the 8080 is trying to do is when it wants to access an input device to read data from an input device, you have to do an input command and then stipulate which input address you want to get the information from. You want to input the information from, that is. So you then follow it with some number between 00 and FF, and it will contrive to go out and get that and then put it in the accumulator. Now, if you wanted to take something from the accumulator and send it to an output device, you do it the same way, but you use the out function or out command instead of the input command. And you do the same thing. You follow it with a number between 0, 0, and FF to stipulate which of those 256 output devices you want to send the data to that's coming from the accumulator. So that's the idea, but how does it do it? Because the 8080 has no pins on it to communicate with external I/O. So how is it doing that? Well, it's doing it through a sneaky way. And to do that, to understand that, we have to understand how the 8080 deals with its status bits. As already pointed out, there is an 8-bit group of status bits that can be thought of as being bundled together as a byte of status information. The 8080 contrives to set its various control lines in a particular combination at a particular time in its machine cycle, so that external circuitry can look at the 8080's data bus and say, when I see that particular combination of control lines at that particular time in the 8080's machine cycle, I will grab that information and store it in hardware as the status byte. So that's how it's done. You have to have external logic looking at the data bus and triggered by a particular combination and timing of pins that are on the 8080. And from that you can capture, in a latch or a memory device, the 8 bits of status. Those 8 bits of status are also used to control 8 LEDs on the front of the Altair or the IMSAI computer. Those are the status LEDs. 2 of those status bits are input and output. So that is where the commands come from to tell external circuitry when to treat the information on the data and address buses as data coming in from an input device or going out to an output device, instead of data coming in from memory or going out to memory, which would be the normal situation. So we have to have at least an IC and some logic tied into the 8080 in order to capture the status byte, and then we have to look at 2 bits on the status byte to see if the 8080 is currently doing an input or an output function, and half of the address bus at that time is used to provide the 8 bits of I/O address. So again, it's not intended for memory, it's intended for the I/O devices that are being controlled through these special instructions. So then you might set up, for example, some logic to look at 8 bits of the address bus and also look at the input or output bits in the status word, and also look at the read and write commands, which are pins on the 8080, and use all those together to say, okay, let's set up the external logic to pipe in 8 bits of input to the data bus, or send out 8 pins of data out the bus, always coming into the accumulator or coming out of the accumulator, depending which way we're going. So I hope that made sense. I didn't see a good way to diagram it except just to talk it through. But that is what is happening. So when we get to this input command, it's followed by FF, which is the highest possible input function address. And the Altair and the IMSAI are hardwired to have the upper 8 address switches, out of the 16 address switches there are, the upper 8 of them, which happen to be positioned right above the upper 8 bits of the address bus on the LEDs, that is. So the LEDs are above the switches, which makes it easier to correlate them to each other bit to bit. So in addition to being used by the address bus to set them using those switches, those 8 switches are also used through extra circuitry to be piped into the data bus whenever the input function is active. And in that way, the 8080 can read in those 8 switches their status and put it in the accumulator. Now what do we do with that? Now that we've captured the user's input, whether any of those switches are raised or not, or which switch and when, we have to compare that to the data in the D register. Remember that the D register is the data that represents the LED pattern. Going back to my other sheet here, let's say we had that first bit on, and it's scrolling, so pretty soon it's maybe here. And pretty soon it might be over here. I haven't gotten to how it gets that way yet, but because we know that the LED is scrolling, we're knowing it's going to be moving in its position from left to right. And we also know there are 8 switches below these. These are the upper 8 address switches, which are also the sense switches that are read by the input function. And our goal will be to wait till the LED gets to some position, whichever one we're eyeballing, and then raise the associated switch for that position right when the LED is on above it. So if it's at this position, we want to be turning on the 3rd switch. If it's over in this position, we want to turn on the 6th switch, and so on. Part of the trick of the kill the bit game is that the LEDs are still moving across pretty fast. They're not on for very long, and they're moving across at a pretty good rate. We have to be really quick and coordinate with our eye and kind of lead it, so you kind of get a feel for how fast they're moving across, and you realize that from the time your brain gives the command to move your fingers to move the switch, some time will go by and maybe the LED will be in a different position. So it's like, you know, shooting with a gun. You're leading the target a little bit. That's part of the challenge. So if you do turn on the switch at the right time, you're going to cancel out that bit and thereby kill it. But if you turn on the switch at the wrong time or in the wrong position, instead of killing the bit, you're going to add another bit to it. So now you have a more complex pattern of LEDs going across, and it can get more and more challenging the klutzier and klutzier you are. So how do we accomplish that killing of the bit? So let's say the D register currently has, I'll assume the LED is moved this far. That means the D register, instead of having 8 0 hex in it, now has 1 0 in it. So let's just assume that it's moved to the point where D now holds 10 hex instead of 8 0 hex. Then I want to turn on that switch so that that switch value gets moved into the accumulator, and that it also has a value of 1 0 hex. Then we want to compare these two with an exclusive OR. What's an exclusive OR? Well, most of the viewers will know what that is, but in logic, if you OR something together, for example, a 0 and a 1, in an OR function, it's just saying, hey, if either of those are on, the output will be 1. What if I had 1 and 0? Same thing. If we OR those together logically, we get a result of a 1. But because it's exclusive, a regular OR, if you had, for example, this, a regular OR would give you also 1, because it doesn't care that both are on as long as one of them is on. An exclusive OR, however, says we're exclusive. You can't do that. If both of them are on, then the answer is 0. By the same token, if you have 2 zeros and you exclusive OR them, the result will still be 0. So this is good for pattern matching. If the switch data happens to match the D register data at the same time, when we do an XOR on them, the result will be 0 if the pattern matches. If the pattern does not match, then we'll be in one of these situations, and we'll be turning bits on. But like I said in the example, if this is the pattern I have and I turn on the switches to this same pattern at the same time, when you exclusive OR those together, these two cancel out and the result is all zeros. I can't write worth a darn this way, sorry. It's sloppy. This would be the result, and therefore you have killed the bit because it's no longer in the D register and it will no longer turn on any LEDs. However, if you screw up and you had, instead of this situation, maybe you turned this switch on instead of that switch, now you're XORing a 0 and or 1 here in the D register with a 0 from the switch, and the result will still be a 1 in that position. And now you're comparing a 1 in the switch with a 0 in the D register, and the result of that will be a 1. So now that gets turned into a 1, and now you've got 2 bits in the D register that are on, and therefore 2 LEDs in the scrolling pattern. That's the way that works. So returning to the program listing, we've got this XRA command immediately following the input command where we get the data from the sense switches. And it's going to XOR register D with the accumulator. Remember, the accumulator is where the switch data is, and put the results in the accumulator. So just like I diagrammed, if we successfully match the switch to the LEDs, which again reflect the value of the D register, then we'll end up with a bit that was a 1 being turned to a 0. And if that was the only 1 in the D register, then we have killed the bit. We have won the game. Well, now that we've done that, we also have to accomplish the scrolling functionality. So we do a RRC instruction, that's rotate right accumulator. So it takes the accumulator data, whatever it is, and rolls the pattern to the right. It rotates it to the right and rolls over the least significant bit to the most significant bit. So back to my diagram. Here's the accumulator. And let's say I had this bit pattern in there. 0, 0, 0, 0, 1, 0. Oops, I didn't make enough positions. I definitely didn't make enough positions. Okay, so I've got this pattern in there. 0, 0, 0, 1, 0, 0, 0. And I want to scroll that to the right. So the rotate right instruction takes all these bits and pushes them one position to the right. Whatever bit is here, whether it's a 0 or 1, is going to get pushed off the right side, but the rotate right instruction loops it back around and sticks it in the leftmost or most significant position, which by the way has just been vacated because that value is already moved to the right. So it's just like moving them in a circle, one position. So now we take that one and we moved over to here. So that's what's happening there. Remember that the accumulator has a copy of the D register. It's not the D register itself. It's a copy of what was there after XORing it and rotating it right. And we need to get that information back into the D register so the rest of the program can use it. The accumulator is busy. You can't store stuff in the accumulator. So we've just worked on it in the accumulator. Now we got to get it back into D for storage. So that's what this move instruction does here. It doesn't have any arguments after it, no data. It's a particular type of move instruction. There's actually move instructions for every register. So this particular move instruction, the one controlled by opcode 57 hexadecimal, means that that move instruction is associated with the D register. So it'll move from the accumulator into the D register, and now the D register has that same data in it. The XORed and scrolled or rotated version of the bit pattern. So now that we've done all that, we're ready to start all over again. So it's followed by an unconditional jump. That means it doesn't care whether there's been a carry or not or some other event. It's just always going to jump. And we have to stipulate the full address. Once again, low bit, high bit. So if you write it out at 0008 hexadecimal, we remember that address because that's the point we've identified previously as the beginning of the active program. So basically you've done that move to D and you just jump right back up to this point in the program, immediately take whatever's in D, write it out to the address bus, and thereby turn on the LEDs. Do it 4 times for persistence of vision. Increment, or not increment, but increase the value in H and L by adding the B and C value to it. Check to see if that resulted in a carry. If it does not, go back and repeat again so you're in that timing loop. Once you bust out of the timing loop, when you've maxed out the H and L value, now you can read in the switches again. You can XOR it with the copy of D that's in the accumulator. You can rotate right the accumulator. You can copy it back to D, jump back up to here again and do it again. So that's what's happening over and over, and it's really that simple. The only things that are really tricky about this program, I think, are why is this being done and how are we getting the computer to turn on its address LEDs under computer control. Well, of course, the only way you can do that is as I already described. You have to fool it into doing that by deliberately accessing a memory location that has that pattern of bits on in the address bus, and then doing it enough that it becomes visible instead of just infinitesimally small flicker that you would never see with the naked eye. And then time delay it so that you do this often enough that it seems to move the LED across as a result of the rotate right at a rate that's good for gameplay. Now, the only thing in here you're likely to change is if you decide the game is just too hard. When you enter this program, you could go here and change not the 80, that's the initial bit pattern, but this value in registers B and C. Like I said, it starts out with 000E. That's a small value in binary terms. If you make that into a smaller number than E, perhaps 000A, for example, would be something a bit smaller. Because it's smaller, it increases H and L by a smaller amount every time it does the loop. Therefore, it takes longer to get out of the loop. Therefore, it does the rotate right less often. Therefore, the scrolling seems to be slower. But if you took 0E and bumped it up to a higher value, perhaps maybe 10, so 0010 would be your complete value here. Now that's a larger value. It's going to increase H and L every time it comes around, and it's going to therefore overflow and result in a carry bit sooner, and therefore it's going to spend less time in the loop, and it's going to do the scroll sooner than it would have otherwise. So this is your speed control bit. This right here that ends up getting put in the B and C registers. You fool with that number. You probably only want to fool with the least significant byte of it, this part, not this part. If you start messing with this, the game will run so fast you won't even be able to tell the LEDs are scrolling. It'll just be screaming by. But you can mess with these numbers a little bit and thereby dial in the speed that the game seems to be operating at. You don't have to start out with the leftmost bit either. If I put in, for example, 08, now I'd have a 00001000 bit pattern instead of a 10000000 pattern. It doesn't matter. as long as you start out with one of the bits turned on, and only one of the bits turned on, any hexadecimal value here that turns into a binary pattern with only a single 1 in it would work. But it just seems cleaner to start from the left side, so that's why 80 hex was picked. And you don't actually have to start out with 0, 0 here, preloading H and L. You could start with some other value. It'll work out the same way. The user won't know the difference. Now, something I wanted to mention earlier, there is nothing in here that resets the H and L registers. It overflows, but it doesn't get reset back to 0, which is what you think you might want to do. But Dean McDaniel, the guy who wrote the Kill the Bit program, realized that so one of the things that's going on in here that I initially figured out incorrectly and then thought about some more and realized something else was going on is how the program is dealing with not having to reset the H and L registers back to 0 every time we have exited the time delay loop. In other words, when we've incremented H and L by adding 000E to it over and over and over until it overflows and sets the carry bit, which then exits the loop. It might seem obvious that you'd have to reset the H and L registers before you start again, or you would already have a high value and it wouldn't count the same amount of time or to do the same number of loops the next time around. However, the function we're using to do addition to increment or increase the value in H and L is the DAD function, which is a 2's complement addition function. It's not using regular binary, it's using 2's complement binary. 2's complement binary is a way to handle signed math. So let's say we had a 4-bit word, right? It's got 4 bits to it. In normal binary, we could use all of those, and you could count all the way up to 8 plus 4 plus 2 plus 1. It could count up to 15 if all those bits are set. 15 decimal. But in 2's complement, we have to take the most significant bit and treat that as the sign bit. If it's set to a 0, then it's a positive number represented by these 3 bits. However, if this bit is a 1, then this is a negative number, and you can't treat it the way it is. You have to invert all the bits and add 1 to get the actual decimal equivalent. It actually makes all sorts of sense for doing mathematics or arithmetic using binary numbers. I won't get into all the reasons for that here, but if we're treating this as 2's complement, now it's really only a 3-digit number with a sign bit added onto it, but that is not part of the number. So in this case, we could only count up to 111, which is 4 plus 2 plus 1, that's equal to 7 decimal, and any higher than that, and we've overflowed. Or another way of looking at it is we would overflow to, if we added something to this, 77 or 111 is equal to 7 decimal, and we can't have a bigger number, but if we added, for example, 1 to that and pushed it over, in pure binary we would have this number here. It would become an 8, but because this is a sign bit and not a value bit, now we have to treat this as a negative number. And to convert it into 2's complement, we invert all the bits here to all ones, and then add a 1 to it to get the equivalent decimal value. So this would again be 7. If you add 1 to it, it's an 8. So this here is equal to an 8, but because the sign bit is turned on, it's a -8, not a +8. So that's the way the 2's complement math works, and we have to bear that in mind when we analyze what's going on with the continued incrementing or increasing of the H and L registers while in a 2's complement math environment. To illustrate that a little better, I've done an exercise here using only 3 bits, just to keep it simple and not have to do too many iterations. I wrote here on my sketch, calculating 2's complement addition on a 4-bit 2's complement binary word, which is really 3 numerical bits and a sign bit, to keep it simple. However, you can extrapolate this same idea to 16-bit 2's complement math, which is really, again, 15 numerical bits and a sign bit. And that's what exactly we would have in the killed bit program using the 2 byte H and L register and adding up to it. And in the kill the bit program, the default increment value or increase value is hexadecimal 000E, which is 14 decimal. In this example, just to keep it simple, I'm only incrementing by a value of 0011 binary, which is 3 in decimal. So we're starting with 0, we're adding 3 each time. Every iteration we're adding 3. So let's just look at it in binary. Now to do this math, you really can just follow normal binary addition rules. You just have to keep in mind that the most significant digit is a sign, not a numerical value. So we start out with 0000. I'm just calling that's the value in HL. Pretend like it's a 16-bit word, but we're only looking at a quarter of it here. And you add 0011, which is a 3. So we're starting out with a 0 decimal in H and L, and we end up with a 3 in H and L. That's 3 binary and 3 in decimal. 0 plus 3 is 3. Boom. It adds up. The math adds up in binary. It adds up if we're doing it in decimal. Now let's add 3 to it again. A 1 and a 1 is 10 binary. So you put the 0 here, carry the 1, and now you have a 1 and a 1, which would be 10, but we've carried the 1, so it's 1, so the 1 goes here, you carry the 1 up here, 1 plus 0 is a 1, 0 and 0 is 0. So that's pure binary arithmetic or addition. We can look at that and see that's 4, 5, 6, so it's 6 decimal. And we know we can treat it as a positive number because the sign bit is not set. If you look at it in decimal, we're taking the 3 that was already there, adding 3 to it, and you get 6. So doing it in decimal, it adds up. Doing the same thing, adding 3 more to this value, 6 decimal value. Now, well, 6 plus 3 would be 9, but in binary, 9 requires the 4th bit to be turned on. It would do like this. So 0 and 1 in binary is a 1. 1 and 1 would be 10. You put the 0 here, carry the 1. 1 and 1 plus 0 is 0, 1, and you have a 1 carried up to here. That plus the 0 comes out to 1. But it's not a number, it's a sign bit, so that means it's a negative number now. We have to treat that as a negative number. If you invert all the bits, that's 1, 1, 0, so that's 4, 5, 6. And then you have to add 1. That's the rule when converting 2's complement. So you add this 1 to the 6 and you get a 7. So it's a minus 7. And that's exactly what you would get, but not in decimal math. In decimal math, it isn't, but we have to treat this as a -7 because we know what that is according to 2's complement rules. So continuing on, we're adding 3 to it again. 1 and 1 turns to 1, 0, so you put the 0 there. 1 carried plus 1 is 1, 0. The 0 is here, you carry the 1. 1 and 0 is a 1, and the 1 and the 0 is a 1. So it's 1, 1, 0, 0. And if I convert that to 2's complement, or from 2's complement binary to decimal, it's a -4. If we look at it in terms of decimal math, you've got a -7 from before. You're adding a +3 to it, which gives you a -4. So that adds up. Adding 3 again, you get this pattern. You do the math. -4 plus 3 is equal to -1, and sure enough, that's what this turns out to be. And now you add 3 more to it again. -1 from before plus 3 equals 2. And you put a 2 decimal down here. If you do the math here, it works out where you have to overflow. So 1 and 1 is 1, 0. The 0's here, you carry the 1. 1 and 1 would be 1, 0 again, but you've got a carried 1 on top of that, which I haven't marked. So you have a 1 here, and you carry the 1. 1 and 1 is 0. The 1 up here, 1 and 1 is 0. And it all rolls over to you have to have another bit set out here, which is the carry bit. So now the 8080 says, we've set the carry bit. But if you look at the number, the negative or the sign bit is no longer a 1, so it's no longer treated as a negative number. If you just look at this as a positive binary number, that's a 2. So it adds up. You do the math in decimal, you get a +2. You do the math in binary, you get a +2. Or in 2's complement binary, it's still a +2. You add 3 to it, you get this pattern, and that interprets as a 5 decimal. If you do it in decimal, 2 plus 3 is 5, so that adds up. You add 3 more to it again, and now it becomes a negative number, and it turns out that means a -8. And looking at it this way, if you took 5 plus 3, that would be an 8, but an 8 in 3 bits, you can't fit it. So obviously that means you have you can't use the normal rules, and you have to treat it as a 2's complement value, which, if you do the conversion, is of course -8. You add 3 more to it again on the next iteration, and it's like taking -8 plus 3, you get a -5, and that's indeed what you got if you follow the 2's complement rule to convert it to decimal. You add 3 more to it again, it's -5 plus 3 is -2, and once again that's what you would have here. If you want to do a sanity check, you invert the bits. That's a 0, 0, and a 1, and you always have to add 1 for the conversion. So 1 plus a 1 is a 2, bango. But it's -2 because the sign bit is turned on. Finally, we add 3 again. If you do it in decimal, the -2 we had from before plus 3 equals 1. It's a +1 now. And sure enough, the sign bit is no longer set, so this is just treated as normal decimal, and that is in fact a binary 1, which adds up and agrees with the math we did coming in from decimal. So from that you can see that if we have a big number and we keep adding a small number to it, and we're doing it in a 2's complement math environment, that we never have to worry about resetting it. If you look at the bit pattern, it's hard to decipher, but if you look at it in decimal, you're starting with 0, you're getting bigger, but then you get too big, and now you have to treat it as a negative number, a -7 in this case, and we keep adding a positive value to it each time, so now it's a smaller negative number and a smaller negative number, and then it becomes a positive number, and because the sign bit is no longer set, Now we have a positive value. The next time you add a 3, it gets to be a larger number. It becomes a 5. You add it again, well, it would become an 8, but that means turning the sign bit on, so now you have a large negative number. You add a positive number to it, and it becomes a smaller negative number. You add another positive value, it becomes a smaller negative number again. You add the positive value, it becomes a positive result, and the sign bit's no longer set. So now the next time you add 3 to it, it'll become a 4. So the value is going progressively larger, and then because of 2's complement math, it's turning into a negative number which gets progressively smaller, and then it becomes a progressively larger positive value, then a progressively smaller negative value, and it does that over and over and over. But each time it flips, it sets the carry bit. So looking at it in the way that the kill the bit program works, we have that very large value in 16 bits, and of course 15 of that's the numerical part, and you keep adding a small value of 14 decimal or 000e to it, and it'll get to be a progressively larger number up to quite a large value, and then it'll start becoming a progressively smaller negative value, and so on, and repeat, repeat, repeat. So that is how it works without needing to do a reset of the H&L register.